Good afternoon. We'll continue today with op amp. Today, specifically, we'll look at two configurations, non-inverting amplifier, and if time permits, then inverting amplifier configuration. Otherwise, it'll be next class. So let's go to the class notebook. And this is where we stopped. So let's pick up here. Voltage transfer characteristic of a generic op amp. Okay. Let's start with the terms gain. Gain is simply defined as ratio of output to input. It is noted by the letter uppercase A. The gain of a system is simply the ratio of the output to the input. Voltage gain is noted as AV, uppercase A and uppercase V. Similar to voltage gain, we have current gain, we also have power gain. But for the purposes of our discussion, we only need to know gain, voltage gain. Right. CL is closed loop. OL is open loop. Okay. And then AOL, if you kids know what AOL stands for, very famous company, one of the earliest precursors of the internet, America Online, used to make a sound called "You've Got Mail." There's a whole movie about it. Remember? Anyway, here it stands for open loop gain. Right. That company still exists, of course, by the way. Powerful conglomerate. AOL Time Warner, merger of three different companies, or maybe they split, I can't remember. But there was a time when that was one of the major corporations around, and everybody got their emails from AOL Corporation. All right, coming back to our talk. AOL is the open loop gain for an ideal op amp. The open loop gain is typically infinite. For real life op amp, it still is very, very high. So about 100,000 or more. Okay. Other terms, in plus is referred to as a non-inverting terminal. In minus is referred to as the inverting terminal. Okay. So to make sure all these acronyms and terms. All right. Before we again get into the op amps, let me just give a brief overview of what an amplifier is and what it actually does. Let's say you have a small AC signal, right? And then you have a large DC source So what an op-amp, not an op-amp, just any amplifier for that matter, what an amplifier does is it takes energy from the DC source and it gives it the shape of the AC signal. And that's what an amplifier does. Okay. As an example, let's say an amplifier has a gain of 100. If you feed it an input signal of 0.1 millivolts, what output do you expect to receive? 0.1 times 100. All right, forget 0.1 millivolts. Let's just say 0.1 volts, right? So what's the output voltage? 10 volts. If you feed it 10 volts, if you feed 100 volts, now gain is 100. If you feed in 1 volt, you get 100 volts. You feed in 10 volts, you get 1,000 volts. Feed in 100 volts, you get a 10,000 volts. Is that really possible? Not really, because the energy to amplify a signal does not come from thin air. It comes from the DC power supplies that are connected to power that system. And so, just in the most generic of terms, I always like to state an amplifier takes the energy of a DC signal and feeds it, gives it the shape of the AC input signal. Okay. So this AC signal could be in millivolts. The DC biasing voltage could be greater than 5 volts, 10 volts, 15, 20 volts, depending on the system, could be any voltage. And you would obtain a resulting amplified output. Okay, so that energy, amplified energy or amplification energy, comes from the DC biasing sources, which is, in our case, here, VDD and VSS. Okay, VDD and VSS. That's a non-inverting terminal. That's the inverting terminal. Okay. So the property of an op-amp is that it will amplify the difference between the two input terminals. So it amplifies the differential input voltage at in plus and in minus. Okay, in plus and in minus. Make sense? Okay. Okay, so since the energy comes from the DC sources, VDD would place a upper limit, VSS would place a lower limit. In both cases, it's simply a limit or a cap that cannot be exceeded. The energy is restricted to what comes from the power supplies. Also, actually not also, let's look at the output characteristic. So for a op-amp, the output voltage is linearly proportional to the input voltage. V out and V in have a linear relationship. It's simply multiplied with the gain, AOL. If the gain is 10, multiply every single input point or value is multiplied by 10. If the gain is 15, 20, 25, 100, whatever the value is, it results in V out having a linear relationship with Vin. Okay. It is shown as steep because the gain is so large that it is at least 100 or 200 times the input voltage. But of course, as I just stated a few minutes ago, that energy is not infinite. The power supplies place a cap on top of the, not on top, sorry, places a cap on the output. And that cap is VDD and VSS. In this graph, as you see, it does not quite reach the value of VDD and VSS. And that is because a portion or a chunk of the DC voltage supply is consumed within the op amp itself. Right? The op amp consists of numerous several transistors and resistors and other components. And so all of that consumes energy. And so a portion of the DC supply voltage is consumed within the op amp itself. And so the actual upper limit is actually VDD minus that voltage that is required to operate the system. All right, let's see. Okay. All right, so how do we implement a VCVS or a voltage control voltage source using an op amp? Right, so as we said, the output of an op amp can be used to amplify voltages. And if it's used to amplify voltages, we can say that it is behaving like a voltage source. It behaves like a voltage source that is dependent on the input voltage. Hence, we can say it as, or we can classify it as voltage controlled voltage source. So in this configuration, you can see that we have a output that is fed back into the input. So this is an example of negative feedback. Which, by the way, is a very common configuration for an op-amp circuit. Okay. In this circuit is more commonly known as a non-inverting amplifier. Okay, non-inverting amplifier. We had the inverting terminal, which is in minus. You have the non-inverting terminal that is in plus. If we feed the input into the inverting terminal, meaning the source input into the inverting terminal, it is known as a inverting configuration. It's fed into the non-inverting terminal, just known as a non-inverting configuration. I will briefly explain the differences in the output both. All right. Let's say this is our input. This input has positive half cycle as well as a negative half cycle. This is going to be very crude. Okay. If the output follows the same phase as the input, we say it's non-inverted or non-inverting configuration. If it's flipped, then we say output is inverted. This is also known as 180 degrees out of phase. This is something you will study when you do AC analysis in 215. Okay, this is out of phase, 180 degrees out of phase. In simple terms, in terms of voltage, it simply means every positive value is now negative and every negative value is now positive. That means the waveform is 180 degrees out of phase. So those are the two amplifier configurations using an op-amp. Okay. Just to give you a real life example, a inverting amplifier or a 180 degree out of phase signal is used for noise cancellation. Okay. When you take an AC signal and add it to its inverted waveform or its inverted counterpart, the resulting sum is equal to 0. So in noise cancellation or noise cancellation technology, a microphone captures the ambient sound, inverts it, meaning it's 180 degrees out of phase, and adds it to that original input, and the resulting output is 0. And that is the fundamental operating principle of noise cancellation. That's where inverting comes in. Anyway, let's come back to our non-inverting configuration. Input goes in here, hence non-inverting terminal. Negative feedback is fed back into the negative terminal. This is via a voltage divider network. This voltage divider network comprised of R2 and R1, and the midpoint is fed into the inverting terminal. So the voltage here is V out over R1 plus R2. Okay. Yes. Margin of error. Okay, so question being asked is about noise canceling technology, and I think the question is asked is it's not really noise canceling, right? Is that what you? Yeah, it's not 100%. No, the simple reason being that noise cancellation simply is going to pick up the ambient noise, and it's going to invert that ambient noise and feed it back into our ears, and so it seems as if it's canceled out, but it can't block out everything. Only the sounds it can capture. That's it. It especially doesn't work on in aircrafts or inside planes because it's not meant to capture all sounds or all frequencies. It can only capture, let's say, ambient noise like people talking or just general noise that is around us, but not anything else. So no, yeah, it doesn't work in real life. It's not going to work as well it does in theory. All right. So as I was saying, V out, this portion of V out is fed back into the input, and then we obtain an expression where V out is equal to R1 plus R2 over R1 times V in. Okay. On the next few slides, we'll see how this is derived, but this is actually the output equation for the output voltage. A more common form for V out is 1 plus R2 or R1 times V in. So if you're reading up from different sources like a textbook or online resources, this is the more common form. Okay. Let's look at a quick, let's take a quick look at the derivation, right? So op-amp's ideal properties is that, or an ideal op-amp has properties that the input resistance is very large. The input resistance is actually measured from, not measured, but it's defined as the resistance between these two terminals internal to the op-amp. And because of that internal high internal resistance, very little current flow actually goes into the op-amp from our AC sources, okay, from the input terminals. The rest of the current and the energy comes from VDD and VSS. Okay, so the voltage difference does go in, but the current does not. Current input is very minimal. Okay, so we can assume that the input resistance is so large that we can assume it to be an open circuit. And if that is open circuit, that means the current going in is equal to 0. That assumptions, or those assumptions, allow us to actually develop this expression. Okay, so the voltage divider network gives us V in minus is equal to R1 over R1 plus R2 times V out. And that's the expression for the voltage at the inverting terminal, V in minus. I'm going to represent this as F. F can be written as R1 over R1 plus R2, and therefore 1 over F is equal to R1 plus R2 over R1. Okay. V out is the difference between the two terminals times the open loop gain AOL. The differential input is V in plus minus V in minus times AOL. V in minus is replaced with F times V out. And this gives us AOL times V in plus AOL times F minus. V out. We take V out on the other side. Once we take it on the other side, in order to obtain an expression for V out, we move everything back on the right side and we get AOL divided by 1 plus FAOL times V in plus. All right, let's take a pause. Let me know if you have any questions. So it is defined by the manufacturer's data sheet. So it's the question being asked is, what are the reasonable values for AOL? Well, the values for AOL would be found on the manufacturer's data sheet. So real life is not typically infinite, is very high, 100,000 would say at least 10,000 or 50,000 and higher. And then, of course, there are also frequency limitations. The op amp does not have infinite bandwidth. As the frequency increases, the op amp gain starts decreasing. So there is always an upper limit, real life considerations. Yeah. All right. Let's see. All right. Any other questions? Okay. Let's go to the next slide. Okay. All right. F times AOL is going to be very large. So F times AOL is going to be far greater than 1. So this we can ignore. If we ignore that, the term simply becomes AOL over F times AOL, cancels out. The answer we get is 1 over F times V in. 1 over F is R1 plus R2 over R1. And so our V out has a form of R1 plus R2 or R1 times V in. Okay. So V out or V in. It's R1 plus R2 or R1. This we can define as the voltage gain AV. And so voltage gain AV for a non-inverting amplifier using an op amp is R1 plus R2 or R1. Or the more common form that you will encounter is AV is, in terms of the resistances, 1 plus R2 or R1. So by simply choosing the values of these resistances, we can determine what the voltage gain would be for our op amp. These resistors are also sometimes known by other terms. R2 is sometimes known as RF, stands for the feedback resistor. And R1, sometimes described as RI, stands for the input resistor. All right, let's take a pause. Let me know if you have any questions. Then we'll look at the LT Spice simulation. What time is it? 2:40. Any questions? Yes. No, this would be AV. So the open loop gain for an op amp means just the op amp by itself. This output is not being fed back into the input. So it's completely open loop. And this is a circuit we create with external resistors. So this is a very good question. So this is not talking about the gain of an op amp. This is talking about the non-inverting amplifier created with an op amp. So it'd be two different things. So there'll be op amp properties, ideal op amp properties, and then circuits we create with op amps and their properties. And so the gain property of this circuit would be 1 plus R2 or R1. If you didn't feed the output back into the input, it wouldn't, it would be completely different circuit. Yeah. All right. All right, let's look at LT-SPICE simulation of this circuit. Standard op amp from LT-SPICE catalog, LT1457. Feedback resistance of 51K and 2K. So a small portion of the output is being fed back into the input. Power supplies is plus minus 5 volts. Because I get far away to declutter the circuit diagram. Notations VDD. Wherever LT-SPICE sees the same notation, it's going to match it up. There's a sine wave input of 100 millivolts peak to peak. Sorry, 100 millivolts peak. And so it's 200 millivolts peak to peak with a DC offset of 50 millivolts. So 0 volt line is here. Why is this not working? And there is a 50 millivolt DC offset. Right, offset. And here's the output 0 volt line. All right. So with the ratio of the two resistors, we can see the gain is going to be 26.5. So any input we feed into this amplifier circuit is going to be multiplied 26.5 times. If you feed in 1 millivolt, we'd expect 26.5 millivolts at the output. If you feed in 1 volt, you would get 26.5 volts at the output. That is provided, of course, our VDD and VSS have that kind of energy. All right, let's look at the two. This is DC. This is AC. The DC offset is also multiplied by 26.5 times. And so the output DC offset is now 1.3. Let me zoom into this. And you can see that's my output. DC offset of 1.3. Also, if you notice, my AC output is supposed to be 2.65 volts peak, meaning plus 2.65 and minus 2.65. In the positive direction, this is plus 2.65. This is minus 2.65. And then, of course, it is shifted up by 1.3 volts. This is 0 volts. So when it shifts it up by 1.3 volts, you can see the top portion of the output is saturated, or you could say it's clipped off. because it's hitting the upper limit of VDD, which is 5 volts. But of course, it's not going all the way to 5 volts. It's getting clipped at 3.21. Small portion, in this case, almost 2 volts of that power supply is being consumed within the op amp itself. Okay. This is something that I would strongly recommend students simulate at their end, right? This is circuit is provided. You all have used LT-Spice. And so this is something you can easily simulate. You can change the DC values. You can change the AC values. You can also change the VDD, VSS values. See how the output changes in response to those changes. Okay, let's take a pause while you think over this. Yes. So the clipping occurs because, let's say, let me understand the question first. Is your question related to why is it clipping, or is your question asking why is it clipping at 3.2? Okay. So does everybody understand why it clips in general? Right? So technically this clipping should have occurred at what value? No. Clipping should occur at 5 volts. Ideally, because our VDD is 5 volts. Right? But the op amp does not run by itself. The op amp itself has several transistors and resistors and other components inside it. So some energy is consumed by the op amp itself to run the system. Okay. So the output is restricted to whatever is left over. In this case, it is just a shade over 3.2. Okay. Does that answer your question? Instead of clipping at 5, it's clipping at 3.2. The reason it's clipping at 3.2 is because that 1.8 volts is consumed inside the op amp itself. It's kind of like overhead, right? You have this container. We are trying to amplify the signal, trying to fit it inside the container, but it's not fitting, so it gets clipped. But now we are shifting it a little bit even higher. If the DC offset was not there, this 1.3 volts was not present, everything would still would fit inside this container. And the way to avoid this clipping is by increasing our output, or sorry, our VDD and VSS to plus minus 10 volts. So now we are supplying sufficient energy for the op amp to operate, plus for it to amplify that signal. And so instead of clipping, now we have a full range of output. Okay, full range of output. You can see it's like right here, 3 point. Okay, so I would strongly recommend students do simulate this outside of class, and then you can vary the DC offset, you can vary the AC input, you can vary the VDD and VSS values. Did you have a question? That's enough voltage for it to not clip. Yes. more visually, I can, let's see if I can explain. So this, let's say this is plus 5 volts. And let's say this is minus 5 volts. Right? And let's say this is 0. Right? Now, the op amp itself needs some energy to operate. And so let's say that is somewhere over here. So let's call this plus 3.2. And this is minus 3.2. So the op amp itself took up a certain portion, right? So now, if your waveform is at 0 and it fits between these two swings, it will be like this. However, if you now apply a DC offset and your waveform starts here, something like this. And so that top portion is clipped. Does this diagram make sense to answer your question? In the next one, and these numbers, I'm just using them from the simulation itself. Okay. In the next one, instead of 5, now we have plus 10 and we have, let's say, a minus 10, right? So we increase the DC biasing voltages. And so this is 0. And now let's say it still consumes 1.8. So it consumes 1.8. This would be what? 8.2 volts. And this would be minus 8.2 volts. So now our waveform, which is small, even though it's somewhere with an offset, it still fits within. And that's why we have a full range of output. Does that give a clear image and answer? Clear picture? Okay. All right. Any other questions? All right. Let's talk about just 2 more things. So, question asked earlier was about the op-amp AOL and the op-amp properties. And I pointed out that the op-amp has certain properties as a device. And then when we create circuits using this op-amp, those circuits also, the properties will alter and change, and the circuits themselves will also have some properties. So we created a non-inverting amplifier using the op-amp. And we like to say that the non-inverting amplifier configuration also has very high input resistance. Okay. So it has very high input resistance because the op-amp itself as a device has higher input resistance. Plus, we are providing negative feedback. Okay. That means the output is fed back into the inputs. The input is being diminished. All right. So very little current is actually flowing into the op-amp. And so this circuit itself also has very high input resistance. Okay, so non-inverting terminal and inverting terminal for that matter, both circuits will have high input resistance. And the output side, it has very low output resistance. The result of that low output resistance is that it can source or sink high amounts of current to the load without consuming a lot within itself. Okay. So again, because of the op-amp inherent op-amp properties as well as negative feedback, output resistance is always also very low. There's one thing I wanted to show was not show, but talk about was dot step parameter. And dot step allows us to change the values of parameters that are present in an LT-SPICE simulation. So in LT-SPICE, we define a component, and then we use the dot step param command, which is right here, dot step param, to specify different values that needs to be stepped for that component. For our load in this case, we are stepping it from 1K to 250 to 25 ohms or 75 ohms. And LT-SPICE just simulates all three values. Okay, it simulates all three values. All right, this is where we stopped for the previous section. So this is where we stopped here, and then we'll pick up here again on Wednesday. All right, I'm here to answer any questions that you may have, but this is where we'll end class for today. All right, any questions from anyone? Yes. I'll address that next session. Yeah. That capacitance is that the input current going into the op amp behaves similarly to a charge capacitor. Yeah. All right. Okay.